All right, so the assignment from 6.1, 1 to 12 and 15, we're exploring the identities, okay, trigonometric identities, and of course the important ones that we went over in the lesson. If you had a chance to view that, you would know that we are talking about reciprocal identities, okay, these three here, the quotient identities involving tan and cotan, and most importantly here, the Pythagorean identities. So cos squared x plus sine squared x equaling 1 is very, very important. The other two stem from that. So we're going to use those in 6.1. Here's some of the homework questions. Okay, so I don't know how you guys did with the homework questions. I trust that you attempted those as you were supposed to. So I'm just going to go over some with you here today, just in case you had trouble with anything or you've gotten stuck. So determine the non-permissible values of x. Okay, so remember from the lesson we talked about you cannot divide by 0, you cannot take the square root of a negative number, that sort of thing. So I don't see any square roots here, so the big thing is we cannot divide by 0, or we can't have a value that makes any trig function undefined. Okay, so and that specifically shows up with tan here, right? This is not in the denominator, but there are values for x that make tan undefined. So we do have to identify those. Let's grab a I think I got a, oh, where's my unit circle here? Let me just fast forward here. This is what we're going to take a look at later today. Here's our unit circle. Let me copy that. Come on back up to these homework questions. Okay, we'll put this down here. So we want to look at the unit circle and check that. I know that's super small. Let me make that a bit bigger. All right, so non-permissible values. So for number 1, okay, in radians, all right, so obviously sine x can't be 0, so sine x is 0 at 0 and at pi, okay? So 0 and pi, okay, those are two, and then if we're making this a general statement, which I probably the back of the book, or they're looking for general statements, so what we would do is we'd start with pi, and we'd say pi plus 2 pi n, okay? Cannot equal any multiple of pi. So that's pi, that's 0, that's 2 pi, that's 3 pi, 4 pi, 5 pi, 6 pi, any of those. Okay? So nowhere else is sine 0, so that's what we're looking for. Pi plus 2 pi n. Okay? Let's just skip over. I'm going to just do a spattering, not all of them, but d here. Let's talk about that d. So tan cannot be undefined, right? Because you can't have an undefined number divided by something. So what can't tan be? Well, we know tan cannot be pi over 2. Right? Because we've got sine. Remember, this is cos theta, comma, sine theta. So it's sine over cos is what tan is. So tan cannot be pi over 2. That's undefined, and 3 pi over 2. So pi, the restricted values would be pi over 2, okay, plus pi n, okay. So pi over 2, you can write it that way. All right. Cannot equal that. And also cos x plus 1, okay, that can't equal 0 as well. So if we have cos x plus 1 cannot equal 0, that means cos x cannot equal negative 1. So where is cos negative 1? I see right here. And that's at 180, or that's at pi. So x can also not equal pi. Okay. And you could do, I mean, if you just did also pi plus 2 pi n, just to kind of say that as well, that's fine. That gives you your pi, and it gives you your, 3 pi and so on. Okay, so I think that might be everything for D as well. So you're just looking at A, where is it undefined? Where are any of the values undefined? And B, where are the values for x that make the denominator 0? Okay. And then pay close attention to tan. You can't tan here in B, right? Cannot be equal to 0 or undefined, okay, or infinity, right? So tan can't be 0 or undefined. So you look at all those x values. All right, so that's number 1, okay. Number 2, why do some identities have non-permissible values? Well, again, like we said in the lesson, its identities are true for every permissible value. So there are some values that are not permissible because of just the way math works. Because values or equations, statements cannot violate rules of math. So you can't divide by 0, you can't take square root of a negative number, as an example. So there are some non-permissible values because we still have to obey all of the rules of mathematics in evaluating or judging or verifying statements. That would be your answer there. Follow the rules of math. Okay, number 3, simplify each expression to one of the 3 primary trig functions. Okay, this is going to be very important when we come to 6.3, which is the culmination really of all of this identity work. We're proving identities. One of the tactics, one of the things that you have to do is to change everything into sine or cos, and you'll be able to kind of like divide out things and simplify things. So this is a very important skill, and really all you have to do is notice like secant is 1 over cosine, and sine squared is, sine times sine, and so on. Cotangent is cos over sine, okay? Things like that. So let's do a couple of those. So each expression, sine, cos, or tan, verify graphically using technology, okay? So we can, I'll do one of those for you as well. So for A, we've got 1 over cos, x, not theta, x, 1 over cos x times sine x, okay? So write in one of the 3, simplify each expression to one of the 3. Okay, so as we simplify this, this actually is sine over cos, right? Sine x over cos x, which is tan x. There you go, for A, okay? And verify graphically. Okay, we can do that. Let's get to the calculator here. I'm going to clear what I have. And so secant, there's no secant button, remember, on your calculator, so you have to do 1 over cos. That's not right. 1 divided by cos, thank you, x, okay. And then I think this silly calculator, I gotta do an overabundance of brackets here. So that whole thing, and then times sine x, okay. So we'll graph that, and I think I'm extremely zoomed in here, but that's okay, it's gonna actually look pretty decent. So does this sort of look like a tan graph? Well, it comes through 0, it kind of has this little curvature, opposite curvature on the other side. The zoom might be a bit strange, but you know what, let's do this. Let's do, on the second line, we'll do tan x, and we'll graph that too, and we'll see if it's different. Now, how do we know if it's the same? Nothing else is showing up here, but the graph could be off screen, so let's just check something. Let's do trace, and we have a cursor here. You see the cursor? And the cursor is on this 1 over cos times sine. And these are my points, 0.17, 0.17. Hey, that's awesome. So let's now use the cursor and go to tan x. The cursor appears to be in the same spot and does have the exact same values. So it looks like it's mapping itself perfectly there. It's the same. Okay, so that's how you can verify graphically. Okay, so that's number 3. And again, chat in if you have any questions here for my live class here. If you have any questions, chat in. I'll address your concerns. But if there is none coming in, I'll just move to number 4. We'll take a look at number 4. So number 4 says simplify, then rewrite each expression as one of the 3 reciprocal trig functions. Okay, one of the 3 reciprocal. So cos, we've got cos, tan, we've got sine. So what we could do is we could simplify this by noticing that there is a factor of tan x on the top and the bottom. The numerator, denominator, those can divide out and give you just 1. And so here then we have what? Cos x over sine x. And if you recall, that is cotangent x. Okay. What about C? Let's take a look at C. All right. So C is cos x over, now this is 1 minus sine squared x. Okay. So let's go back to this key ideas here. So 1 minus sine squared, was it? 1 minus sine squared. Okay. So can you see in the Pythagorean identities here that we have, now these are true statements, these are proven identities, therefore we can actually manipulate those equations because they're equal for all values of x. We can move things around, okay? Which means that I can actually move this sine squared over to the other side, and this becomes this becomes here, it becomes cos squared x equals 1 minus sine squared x. See that? So you can move these things around. And if that's true, then my 1 minus sine squared x right here is actually cos squared x. You see that? And this is extremely important in this chapter. Being able to see this and to rewrite it as this over here. That's extremely important. Okay. And now we have cos over cos squared, or I'm just going to rewrite this. You wouldn't have to show this, but I'm just going to show you. This is what this looks like, right? Cos squared x is cos x times cos x. One of those goes with one of those. They divide out because they're factors. So I have 1 over cos x, which is secant x, okay, for C. And then here, this is all multiplication, so if you write them in terms of sine and cos, I think that would be great, and then you can see that you'll divide things off here and there. All right. Number 5 is about verification. Okay, so simply what you do is you put in 30 degrees and pi over 4 in for x here, and you see if the left side equals the right side. I'll do that real quick for pi over 4. Let's pick this one. So secant is 1 over cosine pi over 4 divided by tan x. Okay, so tan of pi over 4, I can just write that. I know what that is. We'll look on our unit circle there too. Plus cotan of x. Okay, now cotan of x is 1 over tan. So let's just do that. 1 over tan pi over 4. Let's just see, there's a bit of a question mark to see if they're equal to sine of pi over 4. Okay, with me here so far? Tan, cot over, okay. So that's one way you could write that. Now let's just simplify this. So 1 over cos of pi over 4. So pi over 4 has a value, or a point of root 2 over 2 and root 2 over 2. All right. So I have 1 over root 2 over 2, or 2 over root 2. Okay, I'm flipping this. So I'm taking this right here and I'm flipping it around. And on the bottom, I have tan of pi over 4, which is, tan is sine divided by cos. If you have root 2 over 2 divided by root 2 over 2, that's just 1. And over here, I have 1 over 1. 1 over 1. All right. So this is 2 over root 2 divided by 2. Or another way to write that would be 2 over root 2 times 1 over 2. Those 2's cancel out, and I get 1 over root 2. Now, sine of pi over 4 is actually, what is that? Root 2 over 2. But remember, that's a simplified version of 1 over root 2. Because if I simplify this by, 2, by making the denominator a rational, this becomes root 2 over square root of 4, or just plain old 2. So we do have the left side equaling the right side. Okay? And that's a verification. So you have to know your unit circle. You have to be able to add, divide, multiply fractions, guys, okay? Make sure you know how to do that. If you have any questions about that, please ask. Dividing fractions, you take the fraction on the bottom and you flip it and you multiply, right? Multiply it then straight across, top and top, bottom and bottom. Divide by fraction. Okay, let's take a look. I do have 6C already worked out here. I'm just wondering if this is too much of a mess. It might be. To show you just this here, let me just see here. Consider the equation non-permissible, graph the two sides. Okay, could it be an identity? Verify the equation is true. Okay, so again, for number 6, identifying non-permissible values, the denominators cannot be 0, and tan x cannot be undefined or 0. So here we cannot have tan being undefined or 0. Okay? So we've done that already before. Graphing them, so what you want to do is you want to graph them, and if it says this, could this be an identity? What are you looking for? Well, as we've talked about already, we're looking for the two graphs being exactly mapped onto each other. Now, you can't see the whole graph from negative infinity to positive infinity. You can't see the whole graph, but you could zoom out and see if the graphs are exactly the same for as much as you can see. Because what might happen is you may have something like this. All right. Now, I don't know if this is the case with this problem, to tell you the truth, but you could have something like this where you have, a graph like this, looks a little strange, And then you have another graph, and if you just look at this middle part, it looks like, hey, this is exactly the same graph. But then when you zoom out, you notice that something happens. It diverges. Okay? So this could happen. And so if you only look at this part, you say, yeah, it could be an identity. But if you actually expand your screen and say, I'm going to look at the whole, a larger picture, then you can see that they might diverge. And then you'd say, oh, wait a minute. That's not an identity. Okay? It's not true for all possible values for x. And obviously, if we have two separate graphs, x is possible. We can put x into one side and get a value, put x into the other side, get a value. If those values aren't the same, then, then it's not an identity. And then verify. Now remember what exact values are, guys? Exact values. Exact values mean that we don't plug pi or a square root into our calculator and get a decimal. Decimals are approximate answers. So exact values say that we have to include the radicals in our answer. Okay. So it looks like there's some fancy footwork that has to happen here with C. Remember, when we verify, okay, and I'll make this note here, it's very important. When we verify an equation is true, we cannot assume that the equation is true. And I'll talk more about that as we move through this, this chapter. But if you have the left side and the right side, and you go ahead and you add things to both sides, and you divide by the same thing, and you move one thing over here, and you're treating it like an equation. So it's kind of like saying, prove to me that this is true, and you assume that it's true in order to make a proof. That doesn't work, right? Okay? Prove to me it's raining outside. Well, I know that it's raining outside, so therefore everything is wet, and it's and so it's raining outside because I know it's raining outside. That's not a proof. You have to focus on it's wet, it's cool, it's windy and cloud cover, and there's water falling from the sky, stuff like that. Okay, so that's why over here this looks a little strange. You see this down here? Okay, this kind of business down here. So what I had to do is I had to make this side, okay, or actually this over here, I had to make this look like this without moving anything from one side to the other. And that's why this gets a little bit iffy. Do you see what I had to do down here? I had to multiply by the conjugate. Okay, the conjugate. Why? Because on this side there's no radicals in the denominator. On this side there is. So I need to get rid of the radicals over here. I need to rationalize. Okay, so I did that. And then eventually I got the left side to equal the right side. So that's what my work for C looks like. Okay, fill the values in, and then do some manipulation and try and get the left side to equal the right side. So C might have been a challenge for you, but that's sort of what you have to do. Manipulate it so that the left side equals the right side. And that's all the questions that I had planned for you to go over for your chapter 6.1 homework. Maybe you can let me know if you have any other concerns about that for my class online. I'll just pause now and see if there's any other questions.